Alright, hey guys, yeah, so this week we're going to be going through the Princeton test. I'm going to be doing the acid-base section, and Lily's going to be doing the aqueous solution section. I'm not going to do every single question, I'm going to do most of them, but I'm going to just have you do a couple of them on your own, or I'll encourage you to try them. Anyway, let's get started, and apologies if I go a little fast. There's a lot of problems, and I want to touch on them all because they're all really good. I think this is the best test, in my opinion, of all the invites we went to. It's a really excellent test. Yeah. Alright, so let's get started. Let's get started with number 21, which is the first acid-based question. You can read it, but sulfur dioxide is stored in a gas tank at a pressure of 0.75 atmospheres and at a temperature at 25 degrees Celsius. Some of it's dissolved in liquid water, impurity inside the tank, resulting in the formation of sulfurous acid. The equation is as follows. Okay. So, yeah, and I'm just going to kind of explain my thought process a little bit just in case that helps you with your problem solving, because that's kind of the point of this week. Alright, so the first part of the question is, given that the Henry's law constant for sulfur dioxide in water at 25 degrees Celsius is this, calculate the pH of the resulting solution. Okay, so how should we approach this? So Henry's law, we have to use Henry's law. So I'm just going to first convert this to a concentration because it's a pretty simple step. Henry's law is like one of the easiest laws in my opinion. So concentration equals, you can just really look at the units. If this is molars per atmosphere and they give me atmospheres here, if I just multiply them together, I'm going to get concentration. So times, what was it, 0.75, and that equals, hopefully you can see my calculator. Oh, I gotta turn it on, oops. 1.10. Okay, so that's just the concentration of the, let's see what it is, it's the concentration of the sulfur dioxide in the water. So it's the stuff that's dissolved. There's other sulfur dioxide like above the tank, but we don't worry about that because that's not actually in the water, it's not dissolved, so it can't do this reaction. Okay, so, reading the next part of the question, it seems that I want to find the pH, and there's two equations really I have. I have this equation that forms the H2SO3 from the sulfur dioxide, and then I also have that first acid dissociation reaction. Another thing I realized from the kind of the start is that this is a very small Ka2 compared to the Ka1. So in this problem, because all I need to do is find pH, I'm literally not going to worry about this Ka2 at all. Because it's definitely small enough to ignore, right? It's 6 order of magnitudes lower, so we don't have to worry about it at all. So, and that really simplifies the problem a lot. So, so I'm going to write out the two equations and the constants. This is what I like to do in tests. Sometimes in tests I don't have time, but right now I'm going to do it. And this is called acid anhydride, by the way, if you're wondering what that's called. Because it forms acid with water. Okay, K is 2.1 e negative 3. Okay, and then the other equation that we're going to worry about is this dissociation reaction. Sorry if my hand's in the way. Okay. 1.4 e negative 2, that's the Ka for this reaction. What was it? 1.4 e negative 2, okay. Okay, so now I've pretty much written down all the things that I'm given. So now it's really just solving this equilibrium kind of setup here. So from here it really makes sense to me to use Hess's law with equilibrium constants, because look, I have these two things, and if I just multiply these two equations together, I can cross these out completely. And then water's already crossed out because it's not aqueous. So and I only have really three things to worry about. And I know this concentration, right? It's going to be this, because this is going to be in equilibrium with all the other stuff. So the final concentration of the SO2 has to be this, because that's like what has to be dissolved in there by Henry's law. Okay, so I know the final concentration is this. I can cross these two out, and I cross from multiplying the equations, and I can cross these two out just because it's just water. So I'm gonna multiply these equations together to get an equation. I'll write it down like this. I'm just gonna not even put H2O in the equation. Actually, I will just like that. And that forms just these two products. And the K for this will be these two K's multiplied together. So that's going to be 2.1 e negative 3. I hope it's kind of hard to see. I'm sorry. You can just plug it. You can follow along in your own calculator. But that's kind of what we did. Okay. So it's going to be 2.94 e negative 5. Kind of going off the page there. All right. So we've pretty much set it all up, and now it's just a simple equilibrium thing. but it's not. We're not given the initial values at all because this is going to be the final equilibrium value of the SO2. Okay, so this is going to be 1.10. And this is the final. This is like an ice table, but only the equilibrium. Right? It's like the E of the ice table. These two are just gonna. These both start pretty much 0. This really starts at like 1e negative 7, right? Because it's water, but it's essentially 0. So these both get plus x, right? And this is a pretty simple expression to solve. It just gives us 2.94 e negative 5 equals x squared over 1.10. Let's solve for x. Pretty easy. Actually, yeah, let's solve for x. So that's going to be this times 1.1. Actually, I'll just multiply by this one up here that I already have stored. And it's going to be the square root of that. So this is going to be the final concentration of x. So both of these things. So that's 0.00569 molar. And then the pH is just the negative log of this, because this is also the concentration of it is at the end, so we'll just take the negative log of this. Okay. And we're actually going to carry 4 sig figs because if you don't know pH sig figs rule, that's the rule. And if there's 3 sig figs in the molarity, then you get 4 sig figs here. Or actually you get 3 decimal places here. That's really what the rule is. Okay, so the question was, that the question? The question was to find the pH, and we found the pH as 2.244. It's 2.245. Okay. So let's do the next one really quick. And this one's actually super easy, because it says calculate the concentration of sulfite ions. Hey, well hey. We already know the concentration of, it's not the sulfite ions. This is the, see, I almost made a mistake there. They're asking for sulfite ions, so that's the second dissociation. Alright, that's a little clever. So now, the thing is we care about this again. Because before I didn't care about it because we just wanted the hydronium concentration, but now we care about this Ka2 because we want the sulfite ions, so we need the second dissociation. They almost tricked me. So we want the second dissociation reaction, which is going to be, and I write the equations here. I don't often do that on tests because this is kind of a waste of time. It's sometimes useful. It depends if it's like if it's a short test. Definitely write out the equation just to show your work better. But this is a very long test, so I did not do this on the actual test. And the Ka2 is the 6.3 e negative 8. Okay, so this one. Okay, so what is this? These two we actually already have, and because the Ka2 is so small, I'm just gonna write the final equilibrium down, and the minus x is gonna go away. I'm sorry, I'm not showing you. So the minus x is gonna go away from these two things because the Ka2 is just so small. Okay, so this was 0.00569, 0.00569, and then x. Okay, so it's really 0.00569 minus x, and this is minus x. But because this is so small, I'm just crossing that in my head. I'm already doing like the little x part, which is in my head right now. So this gives, and so another thing I can do in my head is this is going to be on the numerator of the expression. This is going to be the denominator, but they're the same value. So they're going to actually cross out again. So x, the final x is just going to be the k, which is I'm pretty sure we said that in some PowerPoint at some point. This is like a rule. If it's the second dissociation, I think this actually might have been the most recent PowerPoint, the one on advanced acid bases. But if it's the second dissociation, it's always just going to be the Ka if you can always do the little x approximation. So that's just a rule you can remember. So it's just going to be the Ka2. It's going to be the final sulfate ion concentration. Okay, nice. So we did this first problem. We did that and we did that. I will mention really quick is I have looked at the answer keys on all of these, and this is the one that I disagree with them on. I'm not totally sure if they're correct or if I'm correct, but you can look into what they did. I think mine's better. But yeah, if you want to see their take on the problem, then go ahead. All right, let's see the next one. So the ammonium ion NH4 plus is a weak acid with K that cobalt ion complex is strong with ammonium to. Okay, so this is a common problem actually, a complex problem with the acid. And it's actually very similar to what we did before, where you're going to have to do another equilibrium Hess's law situation. But yeah, we'll see what you do. So it wants us to calculate the pH, give us some values here, to which this amount of cobalt has been added. Okay, So I'm going to write out the equations again. Sorry if you can't see everything at the same time. Hopefully you remember that. So the first one was NH4 is a weak acid. So that pretty much means you're definitely going to need this equation. And you can see I really do this in my head. Like I think about the equations in my head, but I'm going to draw it out for you. But again, you can't on the test if you have if you think you have time to do it. Be my guest and please do it. So I think it's very helpful actually, or maybe just like whatever works for you, I guess. And this is the Ka equals 5.6 e negative 10. Okay, and then there's another equation going on here, which is the complexing equation when cobalt reacts with ammonia. So, and if you're wondering how I get these equations, I generally know which equations I'm gonna need to worry about by the ones they give you the K of, right? That's a very good assumption to have. And even not, it's kind of clear in this situation. There's weak acids, so you're gonna need that dissociation reaction, and then it also says it complexes, so you're definitely gonna need the complex reaction. So we have cobalt 3 plus 6 NH3. Don't forget the 6. That's very important. Complexes to form complex, and then the Kf is very high. 4.6 E33. All right, so so what we want to do here, and if you're wondering what the NH4I and this thing are, these are just this and this are just both spectator ions because it's going to completely dissociate. So once it's associated in solution, these two anions just don't matter at all. They're not relevant to the problem. Yeah. Okay. So it's kind of clear to me. I think it might take some practice, for you, but it's a complexing problem. Those almost always involve Hess's law, equilibrium stuff. So so I'm gonna combine these two equations, but I'm not just gonna multiply them together. I want the NH3s to cancel out, okay? Because that's kind of that's like my intermediary, right? It's the thing in between. It's the thing that it's not mentioned at all in the problem. They don't give me any values for it. That's definitely the thing we want to cross out. So what I'm gonna do is I'm gonna multiply this equation by 6, and that means I have to put this to the power of 6, right? Because that's how Hess's law equilibrium expressions work. And then I'm going to multiply that with this equation. So my resulting equation is going to be 6 NH4 plus, right, 6 of those, plus 6 H2O, which doesn't actually matter, plus cobalt 3 plus, and that'll go to form, the NH3's cross out, and it'll give 6 H3O plus, plus cobalt NH3, 6,3 plus. Okay? And then the K of this, I'm just going to write it, where should I write it? I'll write it over here. So what's the K going to be? It's going to be, I'll hold it up here so you can see it better. This to the 6th times this, right? So it's going to be 5.6 E negative 10 to the 6th times 4.6 E 33. Alright, so 1.42 E negative 22. So that's a very small K. So not much of this stuff is going to dissociate. And remember, if I had like wanted to flip this equation, or I wanted to divide the equations in some way, subtract them in some way, I would have had to divide the K's from each other. Yeah, and go back to like week 5, I think it is, where we go over multiplying those. And you'll see it's actually, that was kind of an aqueous solution thing then, but now you can see it's very relevant to acids and bases as well. Okay, anyways, get back to the problem. So, make sure I'm finding the right thing. Okay, so pH. So we're calculating pH from these values. I'm gonna, so I'm just gonna calculate the molarity of the cobalt, because they give me moles, and you gotta be careful with this. Sometimes they try to trip you up with the units. They give me molarity of the NH4, but they only give me the moles of this. So I have to do 0.015 divided by the volume of the solution to get that. So that's gonna be, I'm gonna draw it up here. So we have 0.0179 is the cobalt, and then 0.120 is the NH4 plus. If you can read that, hopefully. Okay. So and I hope I'm always keeping it in frame. It's kind of hard to do. Okay. So these are the initial values, right? Because that's how much is actually added to the initial solution. So I'm gonna do the X table in my head again because that's a lot faster. So equilibrium is 0.12. This is the initial NH4 plus. We're gonna minus 6x, right? Because it's a 6 coefficient there. This thing doesn't matter. The cobalt starts with 0.0179 minus x, because there's no coefficient there. This will just be 6x, right? Because there's 6 of them, and this will just be x. Okay. So now you can see we have all the things in terms of x, and so we can easily solve this. Well, easily. Yeah. Okay. So and another thing I can do is I can actually these things can get rid of because look how small that is, right? There's no way that's gonna ever make an effect on these. Even though this gets raised to the 6th power, it's still not gonna matter. This k is just so small. In general, especially whenever on a test you have something that's like wants you to raise it to the 6th, you know you're gonna be able to cross it out because you can't actually solve that, right? So like the test wouldn't ask it if it's like something raised to the 6th power. So you know that you're gonna be able to do this approximation. That's kind of like test tricks you can do. All right. So let's just write this out. So we have 1.42 e negative 22 equals this stuff. So this is gonna be 6 raised to the 6th power times x raised to the 6th power. So I'm just going to write that as 6 to the 6th, right? Times x to the 6th times x. So it's just going to be x to the 7th. Hopefully you understood. That's just like exponent rules. And then we're going to divide by 0.12. It's not really a 1. 0. Right? And this is going to be raised to the 6th power. And I just already got rid of this because we know it's not going to matter. 0.0. I'm just going to do 1/8. Okay. So there we go. Okay, I'm just gonna do this algebra in my head because it's not terribly difficult. So so it'll be I'll move this over here. So it'll be 1.42 e negative 22 times 0.12 to the 6th. Okay, times 0.018. Oh no, that's not right. Dang it. Okay, I gotta restart. There times 0.12 to the 6th, or actually that, times 0.018 divided by 6 to the 6th. Kind of crazy. And then this is just going to be raised to the 1/7. Did you get just x by itself? There we go. There's our x. And it's just algebra I did right there. So that means x equals 1.49 times 10 to the negative 5th. Okay. So that's x, but we're looking for 6x. So H3O plus equals 6 of those, right? So I'm going to multiply by 6. Because it's 6x here, that's how much H is there. That's going to be 1, 2, 3, 4. It's going to be 8.94 times 10 to the negative 5th molar. That's the hydronium concentration. pH is very easy from there. Just take the negative log. Okay. And this is kind of a long problem, but I hope you followed through it all. And it's real. I don't think it's that difficult, to be honest. It's a very clear procedure that you have to do. 4.0048. There you go. It's kind of okay. Boom, we got it. Took a long time, but we got it, right? And often B is a lot easier because we kind of solved this whole thing, right? We solved a lot of parts of this problem. So just like before, where B was a lot easier, B is going to be a lot easier in this case as well, because it's asking calculate the concentration of this complex. Well, we've literally already calculated that. It's X, right? We already have calculated it in the previous problem. So it's like pretty much 5 free points, right? Kind of nice. So we're just going to take this down here, and we'll say X equals the concentration of the cobalt equals 1.49 times 10 to the negative 5th molar. Okay. So we solved this one. We found the pH added by doing our Hess's equilibrium stuff, doing some little X approximations, setting up our equilibrium expression, and then solving for pH and the hydronium concentration and pH. This one we literally could just use a value from the previous part, and it was very easy. So yeah, and I think this is pretty straightforward. I think this is definitely something you should be able to do because this is a pretty common question, relatively common. So yeah, okay, let's move on. Got another whole thing. So 23. We're getting into the thick of it. So a buffalo solution consists of this disodium citrate and 0.4 of trisodium citrate. So we got a bunch of K's there. Calculate the pH of this buffer solution. All right. So this is a pretty straightforward question. Or actually, there's a little trick here, but it's still pretty straightforward. So so let's see. Yeah, I'm gonna be able to move it down so you can see it all. All right. So this is pretty much a rote usage of Henderson-Hasselbalch equation. Okay. You can do it with your equilibrium expressions if you want, but it's just not worth the time at all. Just write down your nice thing and then plug in your numbers. Okay. So it's pKa minus log of acid over base. So pKa. This is, I almost got tricked by this. I think I remember. Because you kind of want to use Ka1, but look, this has already been deprotonated twice. This is Na2C6H607. This is for the C6H807, right? So we don't want to use Ka1. We actually want to use Ka3 because this is going from the twice protonated version, because it's 6 H's, to the 5 H's, and it started at 8 H's. That means it's already been deprotonated twice, and we're just looking for the third deprotonation, which is Ka3, right? So that's actually, I'm sure a lot of people got tricked by that, because that's kind of tricky. You got to make sure you're looking at the formula, because that's actually a clever way to trick someone. I kind of like that, because I didn't get tricked by it. All right, so pH equals the negative log of the third Ka, because it's the third dissociation, so it's 4-7. And then it's going to be minus the log. What's the concentration of the acid? The acid, which one's the acid? This is the acid because it has more H's, obviously. So that's 0.350, okay, divided by 0.480. So this is kind of just a plug and chug thing. So let's do negative log of 4e-7 minus log of 0.35 over 0.48. 6.535. Is that what it asked for? Yeah. Calculate the pH of this buffer solution. That was pretty straightforward, honestly. Henderson Hasselbalch, boom, boom, you're done. As long as you catch the little trick there where you have to use Ka3. So let's move this down. Okay. So the next question is calculate the pH of this buffer solution upon addition of that much to this solution. Alright, so this is a little harder. I would say it's like, there's like 3 types of buffer solution problems, and this is like the second hardest, and the first hardest, well, we haven't seen yet. Okay, so, I can go like this. So, that's not very good. So, anyway. So, I'm gonna write this to 0.125, I'm gonna write this stuff down. Sorry, I'm just writing something below the page where you can't see it. Okay, so I just wrote down the facts they gave us. So so pretty much we had this solution, and they're going to add this much, and they're telling us this was the initial volume of the solution. So one thing I'm going to mention is, this always tricks me up, is there's 2 OHs in this formula. It's barium hydroxide with 2 hydroxides. This is the thing, I get fooled by this so much, you have no idea. This is like my arch enemy. So the number of hydroxides is double this, so we're going to do 0.125 times 2. It's 0.25, right? So that's the amount of hydroxide in the system, and that's really what you care about. You don't care about the number of barium hydroxide. You want to know the number of hydroxide. All right. So what we really need to know is we want to find the amount of these 2 things left after this amount of barium hydroxide is added. And this is a classic buffer solution problem. So we want to find the final molarities of those 2 things. So the initial moles of the acid version of like disodium citrate is 0.350. This is the molarity of it from what they've given us. And then the volume they gave us in this part B was 0.8. And that we're going to subtract, because this is a base, it's going to react with that acid. It's going to react with this disodium citrate. So we're going to subtract the moles of hydroxide, because that's the moles that are going to react. And then we're going to equal, that goes to 0.35 times 0.8 minus 0.25. So it's 0.03. And this is moles. And we're going to do a very similar thing with the trisodium citrate. That's going to be 0.480 times 0.800. Okay? And then this time we're going to add the 0.25. Because why? Because what happens is this amount reacts with this disodium citrate, and then one of the products of that reaction is the trisodium citrate. Okay? I'll write out the reaction really quickly for you. So I'm going to just call this HA. That's the disodium citrate. Plus OH minus, okay, that's this barium hydroxide I'm adding, goes to just water. It's a neutralization reaction. It produces water, and it produces the conjugate base. All right, and this conjugate base is the trisodium citrate. And that's why we add to this, because it's kind of like the X, right? Then like this is the X that's reacting. So we're minus X. This one gets plus X. All right. So this equals 0.48 times 0.8 plus 0.5. 0.634 moles. Okay, so I'm just going to plug this back into pH equals, we just plug it back into the Henderson-Hasselbalch equation because we now know the final moles. And you can use molarity. I could divide both sides by 0.8, but that would be pointless because the 0.8s would just cancel out in this fraction. So I actually don't need to do that, which is kind of nice. So negative log of 4e negative 7 minus log of just the moles over moles, because the same volume solution, so it'll just cancel out, of 0.03 over 0.634. And then pH equals, let's plug that in. Let's do this computation real quick. 4e negative 7 minus the log of 0.03 divided by 0.634. 7.723. Alright. And we can kind of verify this because look how close it is to 6.5. It only goes up like about pH point. And we've added a lot of hydroxide. So this kind of is a quick check just to say, oh yeah, it makes sense, right? Because I remember I think when I was trying to do this the second time, when I was like just preparing for this video, I got like 16 as a pH, so that's like clearly wrong. It would be possible if we just added hydroxide, but because it's a buffer, that would never happen, right? It would never have a pH of 16, so you can kind of mentally check your work, so which is kind of nice. All right, so I think we've done that whole problem. So they asked the pH of the buffer solution. That was just a simple application of Henderson-Hasselbalch, right? Then they asked for the pH again, but this time after we've added some hydroxide, which is the point of a buffer, is that you can add hydroxide and then the pH doesn't change by that much. We do that just by doing finding the final moles of both just through this kind of simple stoichiometry reaction, and then doing another Henderson-Hasselbalch to find the final pH. That's good. So this is a really good practice. So 24 is a titration problem. So I'm not gonna go through it because I think that's something you've already known how to do. There are some tricks in here that I'll let you fall into or figure out. Yeah, but I would really encourage you to try this. If you don't have access to the Princeton test, just let me know. I can give it to you. Yeah, but it should be in the shared folder. But definitely try 24. And it's a very long question. It goes all the way up to F. And I think these last three are actually really good. I kind of wanted to show them in this video, but it's already getting long, so I won't. But this is like the third. This is like the hardest type of buffer question, number E, because they give you a pH and they're asking you to find the amount of base that's added, which is a little more difficult because you have to take a little algebra. So that's a cool problem. Yeah, so definitely try 24. I'm not gonna go through it now because it's very long. But yeah. All right, so we're going to the end, and now at this point we've done all the math. So there are like maybe three math questions, but they're pretty involved. So that's why this is kind of a hard test, because they're like involved math questions that a lot of pitfalls and stuff. And we finally got into the theory. So yeah, so let's read this. So orthohydroxybenzene. Okay, whatever that says. So that's this is the ortho thingy. So salicylic acid, that's this, and this thing, PHBA is this, are isomers of each other. So they have the same structural formula, the same molecular formula. They have different acidic properties. Shown below are the structures. Yes, yes, yes. Please explain your reading for all parts of your picture state your explanation. Okay, I'm gonna just not use those answer sheet. I'm just gonna write right on here because they already have the diagrams. So, an aqueous solution in which the two organic acids has the larger Ka1. All right, so that's pretty much asking which of these two is a stronger acid for the first dissociation. All right, and actually, I when I did this like at actual Princeton, I got all these questions wrong. Okay, like these are really hard theory that it's like kind of obscure theory. So even week 3, I think, when we went through at like acid-base stuff, or like acid-base theory and like how to compare relative acidity, this is still even harder than that. It covers some stuff that we didn't even cover. So don't expect, like, I didn't get it right, like you don't have to get it right. I think it's interesting to hear, but it's really kind of difficult to like. But I'll show you how I think the best way to kind of figure it out would be. So an aqueous solution in which the two organic acids has the larger Ka1. So which is stronger? So when I approach a problem like this, I'm like, okay, what's the difference between the two molecules? That's the best way to go, because that's what matters. Like, it doesn't matter if there's a benzene ring here because they both have that. Like carboxylic acid doesn't really matter, right? So so the only difference is the placement of this hydroxide group, right? So so that's kind of like what's going to matter in this problem. So that actually gives us a really big hint, because that means like it involves not only the fact that there's a hydroxide group, but the placement of it on the molecule. So that's like a really big part of information that we can kind of derive just from looking at the two diagrams and kind of the context of the question. Another thing, so the first thing I would figure out is they're asking for Ka1, and there's actually two hydroxide. There are two H's here that could potentially dissociate. So so which one is it? And that's definitely the first thing you have to figure out. So I think it's kind of obvious that this one on both these will dissociate first because it's on a carboxylic acid. Carboxylic acids are a lot stronger than hydroxide functional groups. So you should kind of see pretty quickly that that this one will be a lot more acidic than this proton. Right. So that keys us in a lot of stuff. So we know that this is going to be acidic proton on each molecule, and we also know that that the placement of the hydroxy group is going to be the only thing that kind of can answer this question. So when we answer it, we're going to have to say something about the placement of the hydroxy group. Okay, and one more thing, kind of going back to our process for how we determine acidity, we don't actually look at the acidity, we look at the conjugate base, right? If you remember this from week 3, you look at the conjugate base, and whichever conjugate base is most stable, that's going to be the best acid, right? Because it's going to want to achieve that stable state of a basic state, right? So really what we're going to do is we're going to on both these, I'm gonna do that, right? So to signify that these protons have been removed. And now what we want to do, and these both have a minus sign on them, is we want to find which of these is more stable. Because the one that's more stable is going to be the one it's a better acid, okay? And when you're answering a question, you want to kind of write some of that stuff down, because the proctor needs to know that you understand that the one that's most stable is going to be, the one with the most stable base is going to be the one that's the most acidic, okay? And then you can get I think I actually probably got half credit on these questions, even though for almost all of them I got even though it's just guessing between two, I almost always got the wrong one, but I think I got even more than half credit just because I wrote down the one that's the most stable as a base will be the most acidic acid, okay? So it's really important that you write that stuff down, because there's a lot of partial, 5 points is a lot of partial credit opportunity. So okay, anyway, so which of these is going to be more stable? I think I probably wrote down something about inductive effect, because this one is farther away, so the electrons would be withdrawn more. And I think it's a very small reason, but the one they give on the test is definitely the correct one, where it's something called intramolecular hydrogen bonding. So what happens here, and I know this is really how would you possibly know this, and you wouldn't. It's just kind of really hard to know. But this one, so what happens is because there's a hydrogen here, it's a lot closer to this negative charge than this one. So this negative charge is stabilized by this, because this is a proton, so it's positively charged. So it's it stabilizes the negative charge because it's so close. So both these oxygens share in this hydrogen, and that stabilizes this negative charge right here and makes the whole base more stable. Whereas here, there's no hydrogen proton anywhere close to this guy to stabilize his negative charge, and therefore there's no way. And therefore this guy's a lot more stable than this one, and that's why salicylic acid will have a larger Ka, because it's the more stable conjugate base. Okay, and again, that's hard to know. I know, it's difficult. Now I think knowing that though, the next two are a lot easier. On my second attempt, I think I got both the next two right. So we've already removed that, but they're asking for the second Ka. So that's obviously going to be this one, right? This is the one getting removed. So which of the two organic acids has the larger Ka? And I think the interesting thing is it's most likely going to be different from the previous question, right? Because why else would they ask that if it was just going to be the same acid? So that's I think these are a lot of tricks that you can use to guess at what the answer will be. But I'm going to be looking for a way to show that this one will have a higher Ka too, right? Because I think that's what they're going to be looking for. I think that's that's just me use in all test taking. So if we remove, now we have to look at the stability if we remove both of these, right? So, and I think what really is helpful for this is drawing all your negative charges. Which do you think is more stable? Okay, now there's no more intramolecular hydrogen bonding because there's no hydrogen anymore. So that throws the window out for that guy. And it comes down to the proximity of these negative charges. Now that there's no hydrogen bond, before that was helpful because there was a hydrogen there to stabilize the negative charge. But now there's two negative charges really close to each other, and that destabilizes the molecule. That's not good. It's simple Coulomb's law, right? They repel, unstable, etc. And so I think this one's a little easier to understand once you know about the intramolecular bonding stuff. And in general, I think this is a lot more common, seeing electron repulsion is definitely a destabilizing effect that I think I've heard of before, whereas intramolecular hydrogen bonding, I've never heard of that. So I think this is a lot more doable. It's really just, it comes down to the electron repulsion between these two oxygens. And that makes this one more stable because this one's destabilized. Either something can be more stable and that makes it a better acid, or it can be destabilized and that'll make the other one a better acid, right? So that means this one's destabilized, this is a better acid, larger Ka2. Okay? So this one is salicylic acid, and this one was PHBA, right? So they're different, just as we kind of guessed with the meta of the question. how would the difference of values for the two organic change if moved to gas phase? So how do these Ka values, the difference, and I think this is, in this question especially, you can really kind of pick apart the question and really go for like, you can really guess at the answer based on the question. They said difference in values of Ka. So first of all, the fact that they're asking means something's going to change with gas phase. So the first thing I think of is, before there were a bunch of waters down here, right? Because it was aqueous, so there's a bunch of water surrounding this. So something about moving to gas phase will cause a change. So that's something very important to know, because, and I think in a lot of these problems, like, what's being changed? What's different? Before we were like, the difference is the placement of the hydroxide groups. That's going to be something about that changes the acidity. Here, all we're doing is changing the solvent. So that means we kind of narrowed down a lot of like what options, what things will result from that, right? And another key thing is, again, they say difference in the values of Ka1. They don't say the difference in like ranking, right? They don't say difference in acidity. They say difference in the values of Ka1. So that makes me think that they're not going to completely switch. Like, this one's not going to suddenly become more acidic than this one, but they're going to change in some way because there's no longer waters there surrounding them. Okay, and I think once you realize that, it's pretty simple. Okay, so I'll erase these two because it's only, we're worried about Ka1, not Ka2. So before there was this hydrogen bonding there, right? And this guy was really unstable. He was much more unstable than this one because this guy had the hydrogen bonding to help him. But this guy was slightly stabilized because of all these waters over here. And I think this is something that you can kind of realize pretty quickly, is because he's really he's stabilized from these waters, okay? Because this is like polar, right? So this guy's stabilized from the waters also, but a lot more from his own hydrogen. But this one's, he really needs the waters to be stable. But if I take away the waters, then this guy's really not stable at all, right? Because he has a negative charge. There's nothing to stabilize that negative charge. This one, there is something to stabilize the negative charge. So he's not like, he still is like, oh, that's not great, I don't have water anymore. But he's still like, I'm okay because I got my hydrogen right there protecting me, stabilizing me. This guy, now he has nothing. So I think that makes it pretty clear that the difference in values of Ka will get greater. This one will become more acidic, this one will become, like, the difference between the acidities will become greater because this guy's even less stable outside of water because he doesn't have anything to stabilize him anymore. Okay? And I think the key in this one was just realizing, what's the difference when I go to gas phase? Like, you're like, what the heck, it changes when I go to gas phase? That's why you're like, I think that's my first thought when I saw this question. I'm like, well, how would it change? But then you just think about the question and you're like, well, what actually is changing? There's no more water. What will that do? And you kind of come to the solution pretty quickly. So, yeah. And that's why I think this is such a good test, because like, it kind of leads you to the thing and you have to think about it, but it's still like, it's doable based on what they ask. Alright, last question. This is kind of a long video, but I think the theory of things are really good. So, we have these two molecules. I'm not going to bother reading this. It's pretty much the same thing as before. Which of the two molecules is more basic? So, okay. This is another, yeah, so this is a little more doable in my opinion. But you gotta kind of think for a second, because it says which is more basic, okay? So more basic means conjugate acid less acidic. Okay, so think about that for a second. That means when I add a hydrogen, and another thing you gotta think about is where would the hydrogen be added, and that's really important for a lot of these questions. You gotta kind of figure out before we had to figure out which one is lost, right? And we realize carboxylic acid because it's a lot more acidic. Here, where will be added? Will it be added here? Definitely not, because this guy's already got a full octet. Even though he's electronegative, where would this double bond go, right? Definitely not there. So pretty much the only other place is here, and that makes sense because NH3, that's a common group, right? I think a little experience in chem will kind of make you realize this. It's kind of similar to the NH4 idea, NH4 plus. So before it was kind of like ammonia, now it's like ammonium a little bit, loosely. All right. Anyway, so back to which of the two molecules is more basic. So that means which of these two molecules, now that we've added the hydrogen and made it as acid, which of these two is less acidic? Okay. Or better, which one's more acidic, and we'll just take the opposite one than that. Okay. So when they ask about basicity, I kind of just translate that into it's really just which is more stable, okay? You can kind of think about it like this, okay, more basic, so which one's conjugate acid is less acidic, so which one's conjugate base of that acid is less stable, and blah, blah, blah. But really what it comes down to is more basic means more stable, okay? So when I remove these hydrogens, I added them just to know where it would go. I remove these hydrogens, which one's more stable? So, the one that's more stable is well, it's this one. I think it's kind of obvious. I think just because when you see electron pair in a ring shape like this, I immediately think resonance. And yes, there's definitely a resonance structure here because this guy can go here, and then there can be an electron pair that hops up over here. And then look, there's an electron pair right there that a hydrogen can come along and get, right? This guy goes over there, electron pair can go right over there. Or actually, sorry, no. That's incorrect. There's an electron pair here. Oh, that was totally wrong. I'm sorry. There's an electron pair here that can slide down here, okay? And then this electron pair can go up here, okay? That's the resonance structure. I'm sorry, I mixed it up. Because there is an electron pair here because there's 3 bonds. Remember, nitrogen has an electron pair always on it. So this electron pair comes down here onto this bond jumps up here, and that's resonant. And that's stable. This one, there's no double bond. There's an electron pair here, but there's nowhere for it to go. There's no resonance structure because there's no double bond anywhere. It can't just hop here because then there's too many bonds, right? So, so this one has resonance. This one is more stable. I think I might have made a mistake before when I said more stable equals more basic, because it's actually the opposite. If it's more stable, it doesn't want to lose that stability by donating a hydrogen, or getting a hydrogen, right? Just like before, the more acidic one is more stable. If its conjugate base is more acidic, its conjugate acid is more acidic because this guy's more stable, his conjugate acid will be more acidic. Therefore, this guy is the answer to the question, because this guy's conjugate acid will be less acidic, meaning he itself is more basic, okay? I know that's kind of a lot to do, a lot to follow. Just think about it. The more stable one won't want to lose that stability by getting a hydrogen. The less stable one, I'm fine getting a hydrogen because I don't have any stability to lose. Alright? So the more stable, less basic, because it doesn't want to lose that stability. Make sense? It kind of takes a little thought. I don't know if you want to follow this train of thought where you kind of like go back to the acid and then like think about which one is more basic from there. You can if you want. It's up to you. Just practice these kind of problems and you're going to get used to it. So this one's more basic because this one's more basic because this one's more stable. So because of resonance. So I would answer like in this question I'd be like, this one's resonance. The electron pair is resonance stabilized, meaning this one is more stable molecule. Meaning this one's meaning it's less basic because it's less likely to want to get a hydrogen to lose that stability. Something like that, and you would definitely get full credit. Okay, final part of the final question. Let's do this. We're at 42 minutes, so let's try to get it under 45. So this molecule is another 5-membered ring compound with a similar molecular structure to these two. Compared to the molecule not chosen in part A, so that means this one is the one we didn't choose in part A because this one is the one we said was more basic. So chosen the one not chosen, this one, is this guy more or less basic than this one? Okay, so this one I think takes a lot of thought. So we're comparing pyrrolinone to this guy, okay? So they're asking which one is this one more or less basic than this one? That's the question. So again, we want to look at the difference between the two molecules, right? An O is here, there's no O here, that's the only difference, okay? So what happens to this molecule to either make it change its basic properties when an O is added? So and I think for this it's really helpful to just draw your electron pairs. But also I think this is a really hard question. I think A is very doable, I think B is a lot harder because it's kind of hard to think about. Anyway, so this one was resonance stabilized, that's why it's more stable. So will this one be more stable or less stable? Will the oxygen stabilize it or not stabilize it? I think my first thought and the natural first thought is, look, there's like there's more resonance structures because it goes, this guy can go here, this guy can go here. That's a resonance structure. That is a resonance structure. But the thing is, that's not related to the hydrogen at all. This resonance structure, it's an added resonance structure, but that resonance structure is there regardless of if there's a hydrogen here or not. So that's not added stability, that's just a resonance structure. Because if it's a resonance structure that's not involved at all with the atom connected to the hydrogen, then it's not going to help that with basicity at all. And I think that's kind of the trap I fell into at the actual Princeton Invitational. What you have to realize is that this guy, there's no resonance this guy can do with this guy because they have a shared bond. So if there's like a carbon here and then to that, then it would work. But they have a shared bond, so like if this one goes here, like how does that help? There's no resonance structure you can draw that involves the oxygen and the hydrogen. And that's the key point. I think at first I was like, oxygen, more resonance, so it's more stable, so it's less basic. Which kind of makes sense, but you gotta realize the resonance structure, the only resonance structure this oxygen adds is not at all involved with the hydrogen, so that's not a reason to say, oh, it's more stable. it actually, on the other hand, it's a reason to say it's less stable because, and this is kind of tricky, when I do this, right, when I do that resonance thing, this oxygen will be connected to like this oxygen will have like is very electron like has a lot of electrons. It's electron like efficient, right? And it's going to be connected to all these other carbons because this guy's over here. It's going to be connected to 3 maybe atoms that are electron deficient, right? And that's going to destabilize the molecule. So the fact that the O is here with a lot of electrons is going to destabilize the molecule because it's going to be surrounded by a bunch of electron deficient carbons. Okay, I know that doesn't make a lot of sense. It's hard to follow. Read the key. They probably explain it better than I do. But this is not something you're really going to need to know. This is, I think, probably one of the most difficult theory questions of the whole test. It's really kind of hard to bring around. I think the easier thing to understand is the fact that there's a resonance structure, yes, but it's not involved in the hydrogen. That's why it doesn't help it be more basic. Okay, I think that's a very key point. So in the end, this one is less basic because the oxygen actually makes the resonance structure destabilized, right? And so that makes that resonance structure less likely to happen, and therefore the electrons are more likely to be stuck here and be able to accept the hydrogen. So that means this one's less basic than this one up here. All right, so there you go. That was the acid-base section of Princeton. I think the theory questions were really difficult. The math questions were a little more doable. And I really encourage you to try number 24, 40-point question, so it's actually a lot of points. And it's not terribly hard, especially A, B, and C. So try that out. I hope this is helpful. I'm sorry it's 45 minutes, but I think this really helps with problem solving and also some of that theory stuff from week 3. Because honestly, that's really hard. Like, kind of figure out acidity and basicity with such similar molecules like this, and these obscure things like intramolecular hydrogen bonding and an oxygen that randomly destabilizes the resonance structure. Like, that's really complicated stuff. So even if you don't totally get it, it's okay because it's the hardest thing I've ever seen on a test. So anyway, good luck on the quiz and good luck this week. See ya.